Greetings and welcome. Today we're talking about a new type of transformation. Yesterday we talked about translations is when you kind of shift an object up, down, left, right, diagonal. And today we're going to talk about reflections. And a reflection is a transformation that uses a line like a mirror to reflect a figure. And the mirror line is called the line of reflection. How appropriate. And so you can see the line M is like the mirror here. A reflection in line M maps every point P in the plane to a point P prime, so that for each point, one of the following properties is true. Okay, so first thing is that P to P prime is going to be perpendicular to your mirror line, okay? And P to the line is going to be congruent to the distance P prime to the line, all right? Or you could say that P to P prime is bisected by the line, right? Like so. That's if the original point was not on the line, and then if the original point is on the line, it just gets reflected onto itself, all right? And that's what this statement is saying down here. Which also, by the way, when you are standing in front of the mirror, perhaps shaving, the twice a week that you do, like I do, the distance you are from the mirror is half the distance you appear to be in your reflection. That you are actually twice as far away from your image as you are from the mirror. True story. True story. Good stuff. And that light is also, you could think the light is traveling, right, twice that distance, so that's another way to think about it. All right, so let's see, reflecting in horizontal and vertical lines. So this is just going to be like a little bit of a practice of some of your algebra skills, coordinate geometry here. Let's see, let's map A, which is over 1, up 3. Yeah, we'll be el más rápido here. B is 5, 2. You guys are master graphers. Which seriously, Lego Worlds, guys, I'm going to be a master builder. It's going to be amazing. There's point C, like so. Does that form a right triangle? No. Right, the slope here is down 2 over 1. The slope here is up 1 over 3. Yeah, so if this was up 1 over 2, then it would have worked, but not a right triangle. So it says to reflect it in the line x equals 3. So x equals 3, the equation of a line x equals a number, let's see, that looks pretty vertical, is going to be a vertical line. All right, here's x equals 3 right here. Ooh. So x equals 3, x equals a number is a vertical line that passes through that number on the x-axis. So notice the 3-ness of that point there. And actually, saying x equals 3 is like saying, give me every point whose x-coordinate is 3. So that does include 3, 0, but also 3, 1, and 3, 5, and 3, -2, and 3, negative pi, right? That all of the points on this line have 3 as their x-coordinate, which results in a vertical line. Now, if I want to mirror this, I'm going to use, I kind of think about this in terms of the properties, where I'm going to measure this distance to the line and go out perpendicular to it in the other direction. So A to the line is 2 units. That means if I go 2 units over here in the opposite direction, perpendicular to the line, this would be A prime. Do you believe it? Yeah. And B is 2 units from the line here, so I'm going to go 2 units still perpendicular in the outro direction, and there's B prime, like so. And then C is 1 unit away, so 1 unit away over here is C prime. Now I realize with my lines there I kind of confused it a little bit, but let me just draw this new triangle. And parts of the triangle did map onto itself, and that's fine. There's the image, and the pre-image is in green here. I don't know. It looks like I just made that way more complicated than it needs to, but it got mirrored over itself a little bit. And also, just some points of interest. Notice that this point from A... Wait a minute. Did I do that right? No, where was B? Ah, guys, B was down here. What am I doing? My green triangle's all wrong. There we go. All right, doot. That line is wrong. Man, classic Waddy mistake. Am I right? There we go. All right, but yeah, what I wanted to point out was that this point on my original triangle got mapped onto itself, and this point on the original triangle got mapped onto itself, because it happened to land in the line. All right, let's quickly graph the same original triangle. So A, B, C. Maybe in the future I'll pre-graph these points so we don't have to just be plotting points all day, you know? So the equation of the line y equals 1, you could think about it as a line with slope 0 and a y-intercept of 1, I think is probably the easiest way to think about it. And so that's a horizontal line, right? So if this is my mirror line, I'm going to... C is going to get mapped onto itself because it happened to be on the line. So there's C prime. A is 2 units above the line, and so I'm going to reflect 2 units below the line. So there's A prime. And B is 1 unit above the line, so I'm going to map 1 unit below the line, perpendicular, and there's B prime. All right, so it's just going to mirror it like so. Let's see, we've got the same starting green triangle and my mirrored triangle, my reflected triangle looks something like that. And that's probably what you would have expected. But I think it's good to think about it in terms of these congruences and these distances and the perpendicular whole thing going for it. It's good to think about it like that. Let's skip on down to example 2. Let's see. Internet friends, we've got a half day today, so we're trying to move quick because I might get to meet some parents tonight. Yeah, hooray. But internet friends, I'm sorry, I'm not planning on ever meeting any of your parents. Maybe I already have, though, if you think about it. Let's see, example 2, reflecting in the line y equals x. Here's a good one, friends. Let's graph FG. So instead of a triangle, here we've just got 2 points. So F is at -1, so left 1, up 2. There's F, and G is at over 1, up 2. Okay. There's G. And there is a segment FG. They told me to make it a segment. I figure I could. What do you guys know about the line y equals x? What does that mean? No, neither. Yeah. What if I think about that in terms of y equals mx plus b? The y-intercept is 0, and the slope is 1, or 1 over 1. And so it's going to actually be the classic 45-degree angle line. It's going to just go up 1 over 1, up 1 over 1, up 1 over 1, or up 5 over 5. This is kind of how I picked my points here. So here's the line y equals x. Meh. There we go. And to reflect, I'm going to be reflecting once again perpendicular to this line. And G to the line is half of a diagonal. So G prime is going to be half of a diagonal in the other direction. So there's G prime. Yeah? And F appears to be 1 and 1/2 diagonals. And so a half and 1 diagonals away is F prime. And I get G prime F prime looks like that, right? And so it's mirrored over that line, and right, our properties were such that these mirrors were perpendicular and bisected by the line. Yeah? And so I like just counting the diagonals of those boxes kind of as a full diagonal, half diagonal, like so. Now, here are some properties, some rules for reflection that will work for kind of some of these standard reflections. To be honest, I don't have these memorized. Yeah, it's true. I actually like to visualize these every time, although if I did have them memorized, these would be shortcuts. Oh, did it not photocopy very well? All right. Maybe I'll recapture the image and reprint it. It might be a little pixelated on your packets. So here this says the following. If A, B is reflected in the x-axis, which the x-axis is the equation of the line y equals 0, all right, then its image is the point A, comma, the opposite of B. Does that make sense? All right, so if I've got a point A here, the only thing that changes when it reflects over the x-axis is its y-coordinate is now the opposite. All right, that's not that bad. Similarly, if AB is reflected in the y-axis, then the image of the point will have the opposite x-coordinate. All right, I'll draw a little picture of that. Why not, shall we? So if I have a point, let's say it's even like over here. Let's say this is like 5, comma, -1. Now it's going to be -5, -1. All right, the only thing that changed is the x-coordinate became opposited, right? Okay, this one's slightly more interesting. If it is reflected in the line y equals x, then its image is the point B, comma, A. The x-coordinate became the y-coordinate, and the y-coordinate became the x-coordinate. Let's actually flip back to this one for a moment and see if that makes sense. So F was at -1, comma, 2, and notice F prime is at 2, comma, -1. It literally swapped the x and y coordinates, right? Or G was at 1, comma, 2, and now G prime is at 2, comma, 1. It just swaps the x and y coordinates. Yeah. And actually, if you think about it, look at the equation of this line. Y equals x, and now the x coordinate is the y coordinate. And the y-coordinate is the x-coordinate. Y equals x. It's just like told you you done swapped it. Yeah, I kind of like that one. Yeah, I like it. All right, and then if you reflect in the line y equals -x, what does the line y equals -x look like, guys? Anyone have thoughts on the line y equals -x? That's going to be a -1 slope passing through the origin. And if I have a point, so let's say I have the point over 1, up 5. I want to do something somewhat exaggerated. So let's say this was 1, comma, 5 in my little sketch here, not to scale. It's saying that the image of the point will be not just flipped, but opposited. Okay, so let's see if I can plot this point. So this is going to be -5, -1. -5, -1. So this is kind of like the inverse of reflections, if you think about it, right? Where we changed the order and opposited both of them, for those of you who are fans of conditional statements back in the day. And yeah, so for perpendicular bisector, that actually does end up working out. So that's kind of interesting. Oh, good. Example 3, we can reflect in that exact line, y equals -x. Reflections aren't that bad. It's going to be good. Here we go. All right, graph FG from example 2. What? I don't remember that long ago. What was it? -1, 2 was F, and G was, what, 1, comma, 2? Was it just that? I think so. I don't have time to find my scroll bar and scroll up. Look, it's hiding so well on me. Yeah, I had it. I'm good. All right, and reflect in the line y equals -x. So like I said, that's a slope of -1, and y-intercept is 0. Man, whoa, look at that. That's like not hitting that corner at all. Actually, if I pick further points, all right, yeah, that's close enough. All right, so let's actually think about this in terms of the new property rather than just the perpendiculars to the lines. So Liam, this point was at -1, 2, right? -1, 2. So yeah, -2, 1 should be where f prime is. And does that appear to be perpendicular and bisected by the line? I think so. I think so, right? That's half a diagonal box away, half a diagonal box away. That done worked. And G was at 1, 2, so this is going to be at -2, -1 for G prime. Right, -2, -1. Yeah, so if I change the order and the signs of each coordinate I do inflect, get a reflection over that line. All right, let's keep cruising, Ooh, here's a postulate. You guys love the postulates. Believe it, because I said so. All right. Here we go. Bam. Guess what? Do you believe this? Well, you better believe it. Not postulates, my friend. We just believe it. Let's see. And so reflections are a rigid motion. Could someone summarize what that means? What does that tell us again? In a reflection, Ryan, Liam, what are your guys' thoughts? If a reflection is a rigid motion, what is that telling me? It means what? What does that mean for these points in these segments or triangles or whatever? Yeah, that these are going to be congruent to each other, that all of their corresponding sides are congruent, all their corresponding angles are congruent. That's what that means. And if I combine two rigid transformations, you can get a composition, and one such composition is called a glide reflection. Look at this one. Well, postulates are believed to be true because they're supposed to be like somewhat obviously true. Oh, all right. And actually, what's interesting about geometry is you could start with a different subset of postulates and then prove back to the other ones sometimes. So it is weird where it behaves that way. So let's see a glide reflection. So those of you who are looking for some sick new moves on the dance floor, this is what you got to do. You do a slide and a flip, right? You do the slide and then you do the flip, all right? Like so. So a glide reflection is a transformation including a translation followed by a reflection in which every point P is mapped to P double prime by the following steps. First, a translation maps P to P prime. Slide, right? And then you reflect it in the line K. It looks as though they happen to choose all parallel vectors with the line of mirror. And then it says, yeah, reflection in line K parallel to the direction of the translation. Yeah, so glide and flip, and glide and flip. There we go. So so there you go. That's not that bad. Let's do a glide reflection. How are we doing for time? We're making it, friends. I think I should just play this video like in the gym, full audio during the parent conferences tonight. It'd be pretty good. All right, example 4. Let's actually have we'll have you guys try this with 0 additional instruction. We'll have you give it a shot, and then I'll come back and have one of you guys walk me through how to do the best, sweetest new dance move. All right, let's. It's prime and then double prime. Double prime, yeah. Oh, yeah, oh, man. What? Yeah, as a naming convention, it does break down after you get, like, past 10, I'm sure. Let's see. A is at 3, 2, so over 3, up 2. Let's see. Oh, those intersections were a little harder to spot. B is at 6, 3, so over 6, up 3 for Bravo. And Charlie is at 7, 1. Charlie. All right. So let's see. Translation. All right, where's the first one go? A is here. What do I do? Where's A prime? It's just going to be 3 minus 12, so that's going to be at negative 9, and still up 2. So there's A prime. B prime was at 6, so that's 6 minus 12 is going to be at negative 6, and then up 3, I think, is what I said. And C prime, 7 minus 12 is negative 5, and up 1. So that's the glide, friends. And now let's do the reflection. The line the x-axis, I guess I don't have to write the equation of that, but that is the line y equals 0, by the way. Let's see how well I can land a 0-degree line. Bam. Landed it. All right, so here's my mirror line, and I'm going to reflect the image to another, newer image. Yeah. Let's see, what's a good color? I guess I'll go purple here. So A is 2 units above, so 2 units below. So here's A dub prime. B is 3 units above, so 3 units below. Here's B dub prime. And C was 1 unit above, so now 1 unit below. C dub prime. Right? Glide, the glidiest of reflections. Lovely. Lovely. All right. Oh, man, I almost forgot this one. Actually, this is good. I don't think I got to this example in my last video. But this is going to be my last one. Example 5. This is actually a somewhat of a change in concept, but it talks about symmetry. And I think you guys have probably seen symmetry in middle school. Symmetry is this idea of ways of mapping a shape back onto itself, and there's linear symmetry, which is what I'm talking about here, and then there's rotational symmetry. So, for instance, right, if I was to rotate this Zelda-style rupee 180 degrees, it would map onto itself, right? But today we're asking about lines of symmetry. So how many lines of symmetry does this have? And notice this. If I was to mirror this over this line, it would map onto itself, correct? That's right, Mr. Waddy. Oh, man, you're the best class. And it looks like I also could mirror it this way. Right? If I midpointed those sides correctly, it doesn't look like I did. That's 2 lines of symmetry, right? Where if I mirrored it, oh dear, I didn't get rid of my ruler. If I mirrored it over that line, the image would flip and look identical after such a transformation. All right, how about the diagonals? No? Right, if I mapped this, it would actually look kind of more like a weird heart shape, I think. Yeah, it would. I don't know. I did it wrong, but you get what I'm saying. So the total number of lines of symmetry in this is 2. All right. How about for B here? I could do the classic up-down. I could do the horizontal Fruit Ninja swipe. It looks like I could go from vertex to vertex. But then I think I could also hit midpoint to midpoint. Infinite? A circle would have infinitely many lines of symmetry. Is it 6? Yeah, I think I should have counted when I drew mine. Because, yeah, I don't want to count each line twice. So, yeah, 1, 2, 3, 4, 5, 6. And if I tried counting this one, you notice that's the same as line 1. So, yeah, so that's 6. All right, how about this one for C? What are your thoughts? Ching. It's not. That's a little better. It's got some slope at the end there, but it looks like one line of symmetry. So not too crazy of a problem. But thanks for watching, internet friends. Have a great day. And once again, remember Ryan's chickens.